Hello and welcome. If you're getting ready for your Financial Management C214 objective assessment, you're in exactly the right place. I know this course can feel like a lot with all the stats and formulas, but I promise it's more manageable than it looks. In this video, we're going to walk through the most important concepts you need to master for your OA. We'll cover descriptive statistics, probability and decision making, the core of hypothesis testing, power of regression analysis, and break-even analysis. Before we dive deep into our first major concept, I want to let you know about something that's going to be incredibly valuable for your exam preparation. I've created over 300 completely free practice questions that work hand in hand with everything we're covering in this comprehensive guide. You'll find the link in the description, and I really encourage you to bookmark it because these questions will help you apply every concept we discussed today. So let's dive right in. Let's begin with the absolute foundation of all quantitative analysis, descriptive statistics. Think of this as learning the basic grammar of data. Before you can write a novel, you need to know what nouns and verbs are. Similarly, before we can make complex predictions or decisions, we must know how to simply describe the data we have in front of us. We do this using two main categories of tools: measures of central tendency and measures of variability. This sounds technical, but it really boils down to answering two very simple, intuitive questions about any group of numbers. First, where's the middle? And second, how spread out is everything? If you can answer those two questions, you've captured the essence of your data. Let's tackle the first question: finding the middle. This is what we call measures of central tendency. These measures give us a single, typical value that represents the center of a group of data. The three key measures you absolutely must know for your exam are the mean, the median, and the mode. First up is the mean, which you already know by its more common name, the average. It is the workhorse of statistics. To calculate it, you simply add up every single value in your dataset and then divide by the total number of values. It's straightforward and uses all the information available in the data. However, the mean has one huge critical weakness. It is extremely sensitive to outliers. An outlier is an unusually high or low value that doesn't fit with the rest of the data. Even one outlier can dramatically pull the mean in its direction, giving you a typical value that isn't really typical at all. Let's look at that in action. Imagine a small startup with 5 employees. Their annual salaries are $40,000, $42,000, $45,000, $50,000, and then the CEO who pays herself $250,000. If we calculate the mean salary, we add them all up to get $427,000 and divide by 5. The mean salary is $85,400. Now, if you told a new hire that the average salary at the company is over $85,000, would that be an honest representation? Not really. 4 out of the 5 people make $50,000 or less. The mean has been skewed or pulled up by that one CEO salary. Here's another example. Imagine 5 students' exam scores are 60, 65, 70, 75, and 100. The mean is 74. It looks okay, but it's still being influenced by that one perfect score. This is why, while the mean is powerful, you have to be cautious and aware of potential outliers. This brings us to our second measure, the median. The median is the true middle value. To find it, you first have to line up all your data points in numerical order, from smallest to largest. The median is the number that is physically in the middle of that line. If you have an odd number of data points, it's easy. It's just the one in the very center. In our salary example with 5 employees, the ordered salaries are $40,000, $42,000, $45,000, $50,000, and $250,000. The middle number is $45,000. That feels much more representative of the typical employee's experience, doesn't it? The median's superpower is its resistance to outliers. That $250,000 salary could have been $2 million, and the median would still be $45,000. Now, what if you have an even number of data points? Let's add another employee who makes $60,000. Our ordered salaries are now $40,000, $42,000, $45,000, $50,000. 60,000, and 250,000. There is no single middle number. So we take the two middle numbers, 45,000 and 50,000, add them together, and divide by 2. The median is now 47,500. This is why you constantly hear about the median home price in the news, not the mean home price. A few billion-dollar mansions in a city would make the mean price astronomical and useless for the average person. The median gives a much more honest picture. A good mnemonic is that median sounds like medium, like the medium strip in the middle of a highway. After tackling the mean and median, you'll find the practice questions I've put together to be a great way to solidify your understanding. They cover scenarios where you have to choose the most appropriate measure, which is a key skill for the C214 OA. You can find them at the link in the description. Our third measure of central tendency is the mode. The mode is the simplest of all. It is the value that appears most frequently in the dataset. That's it. In our original salary example, no number repeated, so there was no mode. Let's look at daily coffee sales at a local cafe for a week. 105 cups, 110, 110, 115, 120, 120, and 120. The number 120 appears 3 times, more than any other number, so the mode is 120. A dataset can have more than one mode. If 110 had also appeared 3 times, the dataset would be bimodal, with modes of 110 and 120. While the mode is easy, it's often the least useful measure of the 3 for financial data, but it's very useful in other business contexts. For example, a shoe store manager would use the mode to find out which shoe size is sold most often, so they know which size to stock up on. They don't care about the mean shoe size, they care about the most popular one. Now let's move on to the second big question. How spread out is the data? This is where measures of variability, also called measures of dispersion, come in. Knowing the centre is only half the story. Imagine 2 cities. Both have an average daily temperature of 75 degrees Fahrenheit. In City A, the temperature is always between 70 and 80 degrees. In City B, it can be 50 degrees one day and 100 the next. Same average, but a completely different experience, right? City A is consistent. City B is volatile. Measures of variability tell us this part of the story. The most important measure of variability, and a concept you must master, is the standard deviation. Conceptually, the standard deviation tells you the typical, or average, distance of each data point from the mean of the data set. A small standard deviation means most of the data points are huddled together, very close to the average. Think of City A. The data is consistent and predictable. A large standard deviation means the data points are scattered far and wide from the average. Think of City B. The data is volatile and unpredictable. In the world of finance, standard deviation is the single most common measure of investment risk. If you're looking at 2 stocks, and both have an average annual return of 8%, you might think they're equal. But if stock A has a standard deviation of 5%, and stock B has a standard deviation of 20%, they are vastly different investments. Stock B is much riskier. Its price swings wildly above and below that 8% average, while stock A stays much closer to it. To really understand standard deviation, we have to quickly talk about its parent, the variance. The variance is actually the first thing we calculate. To find it, you first find the mean of your data. Then for every single data point, you find the difference between it and the mean, and you square that difference. You do this for all the points, and then you find the average of all those squared differences. That's the variance. Why do we square the differences? 2 reasons. First, it gets rid of any negative numbers, so a point below the mean contributes just as much as a point above the mean. Second, it gives much more weight to outliers. A point that's far from the mean, when squared, becomes a huge number and has a big impact on the variance. The problem with variance is its units. If we're measuring salaries in dollars, the variance is in dollars squared. What on earth is a dollar squared? It's not intuitive. And that is why we have standard deviation. The standard deviation is simply the square root of the variance. By taking the square root, we get back to our original units, back to dollars or degrees or whatever we were measuring. So standard deviation is just a more interpretable version of variance. On your exam, remember this relationship. Standard deviation is the square root of variance. If they give you one, you can always find the other. To remember it all, think of mean, median, and mode as telling you the location of your data, and standard deviation as telling you the spread. You need both to understand the full story of any data set. Understanding the difference between variance and standard deviation is critical, and you'll find questions on this very topic in the free practice bank I created. I highly recommend working through them to make sure you've got this down cold. The link is in the description. Now that we can describe data, let's talk about using it to make decisions when we're faced with an uncertain future. This is the realm of probability and decision analysis. At its core, probability is just a number between 0 and 1. 0 means an event is absolutely impossible, and 1 means it is absolutely certain to happen. In the business world, we almost never have the luxury of certainty. Our world lives in the decimals between 0 and 1. We talk about a 70% chance of a project succeeding, or a 20% chance of a recession next year. Our job as managers is to use these probabilities to make the most logical and profitable decisions. One of the most powerful visual tools for this is the decision tree. A proper decision tree has two kinds of nodes, or points. First, we have decision nodes, which we draw as squares. A decision node is a point in time where you, the decision maker, have control. The lines coming out of a square node represent your possible choices. Second, we have chance nodes, which we draw as circles. A chance node represents a point where uncertainty takes over. The lines coming out of a circle node represent the different possible outcomes. Crucially, each of these outcomes has a probability assigned to it, and all the probabilities from a single chance node must add up to 100%, or 1.0. So how do we use this map to find the best path? We calculate something called the expected value, or EV, for each and every choice. Expected value is a fancy term for a weighted average. It tells you what the average outcome would be if you could repeat this decision thousands of times. The formula is beautifully simple. For each choice, you go to its outcomes, and for each outcome, you multiply its financial payoff by the probability of it happening. Then you add all those results together. This gives you the expected value for that one choice. You repeat this for every single choice you could make at the start. Once you have the EV for all of them, the rule is simple. You choose the option with the highest expected value. Let's walk through a more detailed example. You're a farm manager deciding whether to plant corn or soybeans. Your profits depend heavily on the weather. It could be a wet year, a normal year, or a dry year. Your agricultural analyst gives you the probabilities. A 30% chance of a wet year, a 50% chance of a normal year, and a 20% chance of a dry year. They also project your profits for each scenario. If you plant corn, you'll make $80,000 in a wet year, $120,000 in a normal year, and only $30,000 in a dry year. If you plant soybeans, you'll make $100,000 in a wet year, $90,000 in a normal year, and $60,000 in a dry year. Let's build the decision tree. Now let's calculate the expected value for planting corn. It's 30% of 80,000, which is 24,000, plus 50% of 120,000, which is 60,000, plus 20% of 30,000, which is 6,000. Add them up, 24,000 plus 60,000 plus 6,000 gives an EV of $90,000 for corn. Now let's do soybeans. It's 30% of 100,000, which is 30,000, plus 50% of 90,000, which is 45,000, plus 20% of 60,000, which is 12,000. Add them up, 30,000 plus 45,000 plus 12,000 gives an EV of $87,000 for soybeans. The decision is now clear. The expected value of planting corn is 90,000, and for soybeans it's 87,000. It's the superior choice based on expected value. The key is to break it down systematically. Expected value is a tool for making a logical, calculated decision in the face of risk. I know these decision trees can seem complicated at first, but they are a very visual way to tackle problems. The best way to get comfortable is to practice. The free question bank I've mentioned has several decision tree problems that will help you master the process of calculating expected value. The link is right there in the description. Now we arrive at what is often considered the heart of inferential statistics, hypothesis testing. I want you to think of this not as a math problem, but as a legal proceeding. It's a structured, formal process for using sample data to test a claim about a population. In a courtroom, a defendant is presumed innocent until proven guilty. This is the core idea. Our starting position, our assumption, is called the null hypothesis. The null hypothesis, which we write as H0, is the presumption of innocence. It's the statement of the status quo, of no effect, no change, or no difference. For example, if we're testing a new drug, the null hypothesis is that the drug has no effect. The alternative hypothesis, written as HA, is the prosecutor's claim. It's what we're trying to find evidence for. It says there is an effect, there is a change, there is a difference. Our job is to see if our sample data provides enough evidence to convict the null hypothesis and reject it in favour of the alternative. The key piece of evidence in our statistical trial is the p-value. The p-value is a probability. Specifically, it's the probability of getting our sample results, or results even more extreme, if the null hypothesis were actually true. Let's break that down. We collect our sample data and we see some effect. The p-value answers the question, could this just be a fluke? Could we have gotten these results just by random chance, even if nothing has actually changed in the real world? A small p-value, say 0.01, means it's very unlikely, a 1% chance, that our results are just a random fluke. This is strong evidence against the null hypothesis. A large p-value, say 0.40, means it's very likely, a 40% chance, that our results could have happened by chance. This is weak evidence against the null. So how small does the p-value need to be for us to reject the null hypothesis? We need a standard for reasonable doubt. This is our significance level, which we call alpha. Before we even start, we set our alpha level, usually at 0.05. This means we're willing to accept a 5% chance of being wrong, of rejecting the null hypothesis when it's actually true. This is called a type 1 error. The final step is the decision rule, and this is the most critical part to memorize for your exam. It is simple and always the same. If the p-value is less than or equal to alpha, you reject the null hypothesis. If the p-value is greater than alpha, you fail to reject the null hypothesis. The little rhyme that will save you on the exam is, if the p is low, the null must go. When we reject the null, we are making a powerful statement. We are saying that our results are statistically significant. It means we have strong evidence that the effect we saw in our sample is real and not just due to random chance. Let's apply this. A pizza company wants to know if a new recipe reduces their average delivery time from the current 30 minutes. The null hypothesis H0 is that the average delivery time is still 30 minutes. The alternative HA is that the average time is now less than 30 minutes. They try the new recipe for a week and sample 100 delivery times. They find the new average is 28.5 minutes. Is this 1.5 minute difference real, or could it be a fluke? They run a statistical test like a one-sample t-test, and the software spits out a p-value of 0.03. We compare this to our alpha of 0.05. The p-value of 0.03 is less than 0.05. The p is low, so the null must go. We reject the null hypothesis. We conclude that the new recipe leads to a statistically significant reduction in delivery time. On your C214 OA, you will almost certainly not be asked to do the complex calculations to find the p-value. Instead, you'll be given a business scenario and a table with the p-value already calculated. Your job is to interpret it correctly. You'll need to state the null and alternative hypotheses, compare the p-value to alpha, and state the correct conclusion in plain English. The biggest conceptual error students make is in how they word their conclusion. Remember, we never, ever accept the null hypothesis. Think of the courtroom again. A jury never finds a defendant innocent. They find them guilty or not guilty. If we fail to reject the null, it doesn't mean it's true. It just means we didn't have enough evidence in our sample to prove it false. This distinction is subtle, but it's the mark of someone who truly understands hypothesis testing. Hypothesis testing is a deep topic, and if it feels a bit abstract, practice is the best remedy. The free question bank I put together includes several scenarios that give you the p-value and ask you to make the correct conclusion, which is exactly what you'll need to do on the exam. Let's now turn our attention to one of the most versatile and widely used tools in business analytics: regression analysis. If hypothesis testing is about answering yes or no questions, regression is about answering how much questions and making specific predictions. Regression analysis is a statistical method we use to model the relationship between variables. In its simplest form, called simple linear regression, we look at the relationship between one independent variable, which we'll call x, and one dependent variable, y. The independent variable, sometimes called the predictor or explanatory variable, is the one we control or the one we think is causing an effect. Things like advertising dollars, hours of training, or temperature. The dependent variable or response variable is the outcome we're trying to predict, like sales, employee performance, or ice cream sales. When we have a bunch of data pairs for x and y, we can plot them on a scatter plot graph. Usually the points won't form a perfect straight line, but they might show a trend. The goal of linear regression is to find the one single straight line that cuts through the data in a way that best represents that trend. This line is called the line of best fit, or the regression line. The magic of regression is that it gives us the exact mathematical equation for this line, which is usually written as y equals a plus b times x. Let's dissect this equation, because every part is important. Y is the predicted value of our dependent variable. X is the value of our independent variable that we're plugging in. A is the y-intercept. It's the predicted value of y when x is 0. Think of it as your starting point or baseline. B is the slope of the line, and in regression we call it the coefficient. This number is incredibly powerful. It tells us the marginal effect of x on y. Specifically, for every single 1 unit increase in our independent variable x, we predict that our dependent variable y will increase by the amount b. If b is negative, it means y is predicted to decrease. Of course, a model is only useful if it's a good model. So how do we measure the quality of our regression line? The most common way is with a statistic called R-squared. R-squared is a number between 0 and 1, and it tells us the goodness of fit. More precisely, it tells us what percentage of the variation in our dependent variable, y, can be explained by the variation in our independent variable, x. An R-squared of 0 means our line is a terrible fit. X explains none of the changes in y. An R-squared of 1 means our line is a perfect fit. All of the changes in y are perfectly explained by x. In the real world, you'll never see 0 or 1. A good model might have an R-squared of 0.70 or higher, meaning 70% of the outcome's behaviour is explained by the predictor. Let's put this all together with a business case. A marketing manager wants to predict the number of units sold, y, based on the company's advertising budget, x. She collects data from the last 12 quarters and runs a regression analysis. The computer output tells her the regression equation is sales equals sign 500 plus 3.5 asterisk, add budget. It also tells her the R-squared is 0.82. First, let's interpret this. The R-squared of 0.82 is high, so this is a pretty reliable model. The intercept of 500 means that if the company spent $0 on advertising, it would still predict sales of 500 units, perhaps from brand loyalty or word of mouth. The slope of 3.5 is the key insight for the manager. It means that for every additional dollar spent on advertising, the company can expect to sell an additional 3.5 units. Now she can make a prediction. If she is given an ad budget of $10,000 for the next quarter, she can predict her sales. 500 plus 3.5 times 10,000 equals 35,500 units. She can also use this to justify her budget requests. For your C214 OA exam, you will likely be presented with a standard regression output from a program like Excel. You must be able to identify the key pieces of information from this table. You need to find the coefficients to build your equation, the intercept and the slope for the x variable. You also need to find the r-squared value to comment on the model's strength. A very common error is to mix up correlation and causation. Regression shows a strong statistical relationship that allows for prediction. It does not by itself prove that X causes Y. There could be other hidden factors at play, but for making practical business forecasts, it is an indispensable tool. Our final major topic brings us to the very practical, day-to-day financial decisions that businesses face. We're talking about break-even and crossover analysis. These are essential tools for understanding costs, revenues, and profitability. Break-even analysis is the process of determining the exact point at which a business is neither making a profit nor a loss. It's the tipping point. To understand it, you must first be crystal clear on the difference between fixed costs and variable costs. Fixed costs are expenses that stay the same regardless of how many units you produce or sell. Think of things like your monthly rent, insurance premiums, or the salaries of your administrative staff. Whether you sell one widget or 1 million widgets, these costs don't change. Variable costs, on the other hand, are costs that change in direct proportion to your production volume. These include the cost of raw materials, the labour directly involved in making the product, and sales commissions. The more you make, the higher your total variable costs. Our final major topic brings us to the very practical, day-to-day financial decisions that businesses face. We're talking about break-even and crossover analysis. These are essential tools for understanding costs, revenues, and profitability. Break-even analysis is the process of determining the exact point at which a business is neither making a profit nor a loss. It's the tipping point. To understand it, you must first be crystal clear on the difference between fixed costs and variable costs. Fixed costs are expenses that stay the same regardless of how many units you produce or sell. Think of things like your monthly rent, insurance premiums, or the salaries of your administrative staff. Whether you sell one widget or 1 million widgets, these costs don't change. Variable costs, on the other hand, are costs that change in direct proportion to your production volume. These include the cost of raw materials, the labour directly involved in making the product, and sales commissions. The more you make, the higher your total variable costs. Let's make this real. You want to open a specialty coffee cart. The cart rental, permits, and insurance cost you $1,200 per month. These are your fixed costs. For each cup of coffee you sell, the cup, lid, coffee beans, and milk cost you a total of $1. This is your variable cost. You decide to sell each cup of coffee for $4. What is your break-even point? First, let's find the contribution margin. It's the price of $4 minus the variable cost of $1, which equals $3. Now we use the formula. Break-even point is $1,200 in fixed costs divided by the $3 contribution margin. The result is $400. You need to sell 400 cups of coffee each month just to break even. Every cup you sell, after the 400th one, will generate $3 in pure profit for you. This simple calculation is crucial for any new venture to understand its minimum sales target for survival. Crossover analysis expands on this idea. It's a technique used to compare two or more options to find the point at which one becomes more financially viable than the other. Imagine you're choosing between two different printing presses for your coffee cart's flyers. Press A is cheap to buy, so it has a low fixed cost of only $500. But it uses a lot of ink, so its variable cost is 50 cents per flyer. Press B is a high-tech model with a high fixed cost of $3,000, but it's incredibly efficient, with a variable cost of only 10 cents per flyer. Which one should you choose? It depends on how many flyers you plan to print. Crossover analysis finds the exact volume where the total cost of both presses is identical. Below that volume, the cheap Press A is the better choice. Above that volume, the higher efficiency of Press B makes it the winner in the long run. On your exam, you'll see story problems describing these kinds of scenarios. Your job is to carefully identify the fixed costs and variable costs for each option and use them to determine the break-even or crossover point. guiding a business to the most profitable decision based on their expected volume. All right, that was an extensive journey through the core of financial management and quantitative analysis. Let's take a final moment to zoom out and see how all these pieces fit together into a coherent whole. We started with the absolute basics of descriptive statistics, learning to describe a dataset using its center, mean-median mode, and its spread, standard deviation. This is the foundation for everything that follows. From there, we stepped into the world of uncertainty, with probability and decision analysis, using decision trees and expected value to bring logic and structure to risky choices. This showed us how to move from just describing the past to making informed bets about the future. Then we delved into the formal, rigorous process of hypothesis testing. This is the scientific method of business, allowing us to use sample data to test a claim about a larger reality, using p-values and significance levels to determine if an observed effect is real or just a fluke. This gave us the tool to validate our ideas. Next, we explored the powerful predictive capabilities of regression analysis. We learned how to model the relationship between variables with an equation, use R-squared to judge the model's strength, and then use that model to make specific, quantitative forecasts. Finally, we brought it all down to the bottom line, with the practical tools of break-even and crossover analysis, which directly address questions of profitability and optimal choice that businesses face every single day. Notice the beautiful progression here. We go from describing data, to making probabilistic decisions, to formally testing our theories, to building predictive models, to making concrete financial choices. Each tool builds on the last. You can't do hypothesis testing without understanding the mean and standard deviation. You can't build a good regression model without being able to interpret the data it's based on. All of these are not just isolated formulas to memorize. They are a connected toolkit for thinking quantitatively and making smarter, more defensible decisions in any field. When you sit down for your C214 OA, take a deep breath. Read each question with care and ask yourself, what is this question really asking me to do? Is it asking me to describe a set of numbers? That's descriptive statistics. Is it asking me to choose between options with uncertain outcomes? That's a decision tree. Is it asking if a new marketing strategy had a statistically significant impact? That's a clear signal for hypothesis testing. Is it asking me to predict sales based on advertising spending? That's regression. You have learned this toolkit. You understand the logic behind each tool, and you are more than ready to apply it. You've got this. Now, the single most important thing you can do to turn this knowledge into an excellent exam score is to practice, practice, practice. I cannot stress this enough. Working through problems solidifies these concepts in your mind like nothing else. That's exactly why I created that comprehensive library of over 300 free practice questions, with the link right in the description below. They are designed to mirror the style and difficulty of your C214 OA questions. Combine the deep understanding you've built today with dedicated practice from that question bank, and you will walk into your exam with confidence and come out with the score you deserve. Thank you for your time and attention today, and I wish you the very best of luck.